So let's look at a method where we can store data and pass data securely, but also to create some resilience in here. The method that we'll be using is the Shamir secret share method, and we'll be applying public key encryption through elliptic curve methods. And overall, we want an efficient method for us to be able to keep secure and also to be resilient. Okay, so the method that we'll be using is elliptic curve cryptography. So it's used in Bitcoin, the Tor network, and many other applications. And it's almost becoming the de facto standard for any public key method. It's used extensively within key exchange at the current time, and most of the connections that we actually make to remote systems are through public key negotiation, are through elliptic curve methods. So with this, we have an elliptic curve, which looks a bit like that. We then define a point G on the curve, and we generate a private key. This is a 256-bit random number and will be kept secret. We then multiply the private key by the G, which is an X and Y point, to find the public key. So the public key becomes an X and a Y point. We can release our public key, and it is extremely difficult for someone to find out our private key, even though they have our public key and the G value. So there's our typical value of G that we have for our elliptic curve methods. So a method that's used extensively to be able to create a shared secret key is what's called elliptic curve Diffie-Hellman, and it builds on the Diffie-Hellman method but uses elliptic curve methods. So in this case, again, we create our public key from our private key and multiplied by G. We also use the mod of an order, so we take a prime number and then every operation that we have is with the mod of that prime number. So I've not shown that in this example, but that will constrain the value that we get here into what's called a finite field. We pass the public key, QA, and Bob passes his public key, QB. And then Alice multiplies the value she gets from Bob with her private key to get the shared value. And then Bob does the same. He takes his private key and multiplies by the value he's received from Alice to get the share. In the end, we have DA times DB times G mod P, this prime number, of course, and we get a shared value which will be the same. So the method that we're going to use is this one here. So Bob and Alice will each create their own public and private key. So this could be per session or per file, or it could be a long-term public and private key. So perhaps Alice wants to store some values that she wants to recover. So she could be Alice on the other end, or she wants to allow Bob access to a file which is stored within a cloud system. So she takes the message or the file, and in the end they'll exchange their public keys to be able to create a shared key. The shared key is then used with the Shamir method, which will split the shares into will split the message into a number of shares. The way it works is that we can have T shares to be able to reconstruct the message back again. So we could have something like a 3 from 5. So we have 5 shares, and then as long as we can find 3 of those shares, we can build back the original message. So this is defined as N shares and T threshold. So in our case, we'll use this standard curve, which is used in Bitcoin and Tor and so on. Bob and Alice agree the G value and the P value. We'll see them a little bit later. Alice creates an A random number. Bob creates his private key as a random number. She will pass that value, and he will pass that value, and then the shared key is AB times G, mod this prime number. So then once they agree on the shared key that they're going to use, Alice will take the secret, and then using the Shamir secret sharing method, she will split it into a number of shares, n. But she will also make sure that we have t threshold, so that t shares could be brought back together to create the original message. So it might be a 2 from 3, say, where we create 3 shares, and as long as we can find 2 of the shares, we can reconstruct the data. She then takes each of these shares as integer values, and then adds on the secret key value that she's computed onto each of the points. So we end up with point 1 as the first share plus AB times G. Computationally, it's not possible for anybody to be able to compute back the value of M from there, even though they watched the conversation between Bob and Alice in the negotiation of the key. So then Alice will send that over, or might store it within a cloud system, and then all Bob has to do is to take his value of ABG and subtract it from the value that he receives. Again, it's all done mod P. From here, he's able to reconstruct all the shares, and then takes T shares to be able to recreate the message again. So this is some sample Python code that you can download from a GitHub. And we're creating the 2 from 5 here with a message of this value. We can create an integer value from our message if we require. And then we create our secret key, our public key, and the shares that we're going to be using S from T and N. So this then creates the secret key. We can then print out the values of our shares and then just verify them here. And then we'll reconstruct the key back again from our shares and T. So we'll take T shares and the shares that we have and reconstruct the original key again, or the original key. After that, we'll have our we can encrypt our message with our public key, and hopefully we can then decrypt them back again once we have our shares. So let's see that in operation. Okay, so we have a 2 from 4 here, and here's the message. So we'll just compute that. Okay, 2 from 4. The elliptic curve we're using is this one here, and we can see that has an X point and a Y point here, and this is our order. So our order, everything is done mod of this value here. So we've created a shared key here, and then we create 4 secret shares, 4 shares. After that, we take 2 of them back and reconstruct the key, and here we are with the message, and we can reconstruct it back again. Okay, so if you're interested, the code is there too. Okay, so our sample run shows this, that we have our G point, there's our order that we're using, 2 from 4, original key, there's the 4 shares, we verify them that they're all correct. We then reconstruct the key back again, and we can get the original message back, hopefully. So here's an example here of how we could use this. So Bob and Alice, remember Alice could be the person actually reading it back, so it doesn't have to be a Bob and Alice scenario here, but we'll make it that Alice is storing some shares on a cloud. So she might select 3 cloud systems, and she puts each share in each cloud. So if one of the clouds fails, then Bob is still able to reconstruct the data from the 2 clouds that are left. So public and private key, they will go the negotiation, there'll be a shared key between them that only they will know. We'll then have a splitter that will split the shares here into 3, and we do an any 2 from 3 share split. Then Bob, when he wants to access the file, will pick 2 of the shares and then do a 2 from 3, reconstruct with his shared key that is negotiated with Alice, and then we'll reconstruct the file back again. So in this way we have resilience because one of the clouds could fail and we can still get the shares back. Because of the Shamir method, it's not possible to be able to read any one share and interpret any data from it. So in this case we get almost perfect security, but we also get resilience in here. Okay, so that's been an outline of how we can use secret shares with elliptic curve methods.